In the name of Almighty God, I am Mahsa Sankosha, and today I want to talk about shell and tube heat exchanger. A heat exchanger is a device that transfers thermal energy between two or more fluids, heating one while cooling the other without direct contact or mixing. These devices are crucial in many applications such as HVAC systems, car radiators, and power plants for processes like heating, cooling, and pasteurization. They can use various mechanisms like conduction through a solid wall or direct contact and come in many forms with shell and tube and plate and frame designs being common examples. And how it works. A hot fluid flows through one part of the exchanger while a cold fluid flows through another. Heat is transferred from the hot fluid to the cold fluid through a conductive material that separates them. This process causes the hot fluid to cool down and the cold fluid to heat up. And the heat transfer happens through a combination of conduction and convection. And what about the common types? The first common type is shell and tube. One fluid flows through a bundle of tubes while the other fluids flows around the tubes in a shell. The next type is plate and frame. Thin plates are stacked to create flow channels for the fluids, which are separated by the plates. And what about the regenerative? A heat storage medium temporarily absorbs heat from one fluid and then releases it to another fluid. A common example is a thermal wheel in a HVAC system that captures heat from exhaust air to preheat incoming fresh air. And what about the key features and considerations? The first one is materials. Heat exchangers are made from various materials including metal like copper and stainless steel, ceramics or plastics depending on the temperature and fluid compatibility requirements. And what about the applications? They are used in a wide range of industries such as HVAC, automotive, and food processing. The next one is flow configurations. The fluids can flow in different patterns relative to each other, including parallel, countercurrent, or cross flow. And what about the maintenance? Some types, like plate and frame, are easier to clean than others. A heat exchanger is a system used to transfer heat between a source and a working fluid. Heat exchangers are used in both cooling and heating processes. The fluids may be separated by a solid wall to prevent mixing, or they may be in direct contact. They are widely used in space heating, refrigerator, air conditioning, power stations, chemical plants, and petrochemical plants, petroleum refineries, natural gas processing, and sewage treatment. The classic example of a heat exchanger is found in an internal combustion engine in which a circulating fluid known as engine coolant flows through radiator coils and air flows past the coils, which cools the coolant and heats the incoming air. Another example is the heatsink, which is a passive heat exchanger that transfers the heat generated by an electronic or a mechanical device to a fluid medium, often air or a liquid coolant. And what about the flow arrangement? There are three primary classifications of heat exchangers according to their flow arrangement. In parallel flow heat exchangers, the two fluids enter the exchanger at the same end and travel in parallel to one another to the other side. In counterflow heat exchangers, the fluids enter the exchanger from opposite ends. The countercurrent design is the most efficient in that it can transfer the most heat from the heat transfer medium per unit mass due to the fact that the average temperature difference along any unit length is higher. In a cross-flow heat exchanger, the fluids travel roughly perpendicular to one another through the exchanger. For efficiency, heat exchangers are designed to maximize the surface area of the wall between the two fluids while minimizing resistance to fluid flow through the exchanger. The exchanger's performance can also be affected by the addition of fines or corrugations in one or both directions, which increase surface area and may channel fluid flow or induce turbulence. The driving temperature across the heat transfer surface varies with position, but an appropriate mean temperature can be defined. In most simple systems, this is the log mean temperature difference. Sometimes direct knowledge of the LMTD is not available and the NTU method is used. And what about the types? By maximum operating temperature, heat exchangers can be divided into low temperature and high temperature ones. The former work up to 500 to 650 degrees of centigrade, depending on the industry, and generally don't require special design and material considerations. The latter work up to 1000 or even 1400 degrees of centigrade. Double pipe heat exchangers are the simplest exchangers used in industries. On one hand, these heat exchangers are cheap for both design and maintenance, making them a good choice for small industries. On the other hand, their low efficiency coupled with the high space occupied in large scales has led modern industries to use more efficient heat exchangers like shell and tube or plate. However, since double pipe heat exchangers are simple, they are used to teach heat exchangers design basics to students as the fundamental rules for all heat exchangers are the same. The first one is double pipe heat exchanger. When one fluid flows through the smaller pipe, the other flows through the annular gap between the two pipes. These flows may be parallel or counter flows in a double pipe heat exchangers. Parallel flow, where both hot and cold liquids enter the heat exchanger from the same side, flow in the same direction and exit at the same end. This configuration is preferable when the two fluids are intended to reach exactly the same temperature, as it reduces thermal stress and produces a more uniform rate of heat transfer. Counterflow, where hot and cold fluids enter opposite sides of the heat exchanger, flow in opposite directions, and exit at opposite ends. This configuration is preferable when the objective is to maximize heat transfer between the fluids as it creates a larger temperature differential when used under otherwise similar conditions. The simulation that you can see here above illustrates the parallel and counter flow directions of the fluid exchanger. Then second issue is shell and tube heat exchanger. In a shell and tube heat exchanger, two fluids at different temperature flow through the heat exchanger. One of the fluids flows through the tube side and the other fluid flows outside the tubes. But inside the shell side, baffles are used to support the tubes, direct the fluid flow to the tubes in an approximately natural manner, and maximize the turbulence of the shell fluid. There are many various kinds of baffles, and the choice of baffle form, spacing, and geometry depending on the allowable flow rate of the drop in shell side force, the need for tube support, and the flow-induced vibrations. There are several variations of shell and tube exchangers available. The differences lie in the arrangement of flow configurations and details of constructions. In application to cool air with shell and tube technology such as intercooler, charge air cooler for combustion engines, fans can be added on the tubes to increase heat transfer area on air side and create tubes and fans configuration. Some design types of shell and tube heat exchanger, fixed tube sheet, floating tube sheet, U-tube, condensers, kettle reboiler, stack type heat exchanger, evaporator, and the third one is plate heat exchanger. A plate heat exchanger contains an amount of tin-shaped heat transfer plates bundled together. The gasket arrangement of each pair of plates provides two separate channel systems. Each pair of plates form a channel where the fluid can flow through. The pairs are attached by welding and bolting methods. The following shows the components in the heat exchanger in single channels. The configuration of the gasket enables flow-through, and thus this allows the main and secondary media in counter-current flow. A gasket plate heat exchanger has a heat region from corrugated plates. The gasket function as a seal between plates, and they are located between frame and pressure plates. Fluid flows in a countercurrent direction throughout the heat exchanger, and efficient thermal performance is produced. Plates are produced in different depths, sizes, and corrugated shapes. There are different types of plates available, including plate and frame, plate and shell, and spiral plate heat exchangers. The distribution area guarantees the flow of fluid to the whole heat transfer surface. This helps to prevent a stagnant area that can cause accumulation of unwanted material on solid surfaces. High flow turbulence between plates results in a greater transfer of heat and a decrease in pressure. The fourth one is condensers and boilers heat exchangers using a two-phase heat transfer system are condensers, boilers, and evaporators. Condensers are instruments that take and cool hot gas or vapor to the point of the condensation and transform the gas into a liquid form. The point at which liquid transforms to gas is called vaporization, and vice versa is called condensation. Surface condenser is the most common type of condenser, where it includes a water supply device. And this simulation displays a two-pass surface condenser. The pressure of steam at the turbine outlet is low, where the steam density is very low, where the flow rate is very high. To prevent a decrease in pressure in the movement of steam from the turbine to condenser, the condenser unit is placed underneath and connected to turbine. Inside the tubes, the cooling water runs in a parallel way, while steam moves in a vertical downward position from the wide opening at the top and travel through the tube. Furthermore, boilers are categorized as initial application of heat exchangers. The word steam generator was regularly used to describe a boiler unit where a hot liquid stream is the source of heat rather than the combustion products. Depending on the dimensions and configurations, the boilers are manufactured. Several boilers are only able to produce hot fluid, while on the other hand, the others are manufactured for steam production. Shell and tube. Shell and tube heat exchangers consist of a series of tubes which contain fluid that must be either heated or cooled. A second fluid runs over the tubes that are being heated or cooled so that it can either provide the heat or absorb the heat required. A set of tubes is called the tube bundle and can be made up of several types of tubes, plain longitudinally confined, and etc. Shell and tube heat exchangers are typically used for high pressure applications with pressures greater than 30 bar and temperatures greater than 260 degrees of centigrade. This is because the shell and tube heat exchangers are robust due to their shape. Several thermal design features must be considered when designing the tubes in the shell and tube heat exchangers. There can be many variations on the shell and tube design. Typically, the ends of each tube are connected to plenums, sometimes called water boxes, to holes in the tube sheets. The tubes may be straight or bent in the shape of a U, called U-tubes. Tube diameter. Using a small tube diameter makes the heat exchangers both economical and compact. However, it is more likely for the heat exchanger to fall off faster, and a small size makes mechanical cleaning of the fouling difficult. To prevail over the fouling and cleaning problems, larger tube diameters can be used. Thus, to determine the tube diameter, the available space, cost, and fouling nature of the fluids must be considered. And what about the tube thickness? The tube thickness of the wall of the tubes is usually determined to ensure there is enough room for corrosion and that fluid-induced vibration has resistance. The next is axial strength, availability of spare parts, hoop strength to withstand internal tube pressure, buckling strength to withstand over pressure in the shell, and next topic is tube length. Heat exchangers are usually cheaper when they have a smaller shell diameter and a long tube length. Thus, typically, there is an aim to make the heat exchanger as long as physically possible whilst not exceeding production capabilities. However, there are many limitations for this, including space available at the installation site and the need to ensure tubes are available in lengths that are twice the required length so they can be withdrawn and replaced. Also, long thin tubes are difficult to take out and replace. And the next topic is tube pitch. When designing the tubes, it is practical to ensure that the tube pitch, for example, the center distance of adjoining tubes, is not less than 1.25 times the tube's outside diameter. A larger tube pitch leads to a larger overall shell diameter, which leads to a more expensive heat exchanger. Tube corrugation. These types of tubes, mainly used for the inner tubes, increases the turbulence of the fluids, and the effects is very important in the heat transfer, giving a better performance. The next one is tube layout. Refers to how tubes are positioned within the shell. There are four main types of tube layout, which are triangular 30-degree, rotated triangular 60-degree, square 90-degree, and rotated square 45-degree. The triangular patterns are employed to give greater heat transfer as they force the fluid to flow in a more turbulent fashion around the piping. Square patterns are employed where high fouling is experienced and cleaning is more regular. A baffle design. Baffles are used in shell and tube heat exchangers to direct fluid across the tube bundle, and they run perpendicularly to the shell and hold the bundle, preventing the tubes from sagging over a long length. They can also prevent the tubes from vibrating. The most common type of baffle is the segmental baffle. The semi circular segmental baffles are oriented at 180 degrees to the adjacent baffles, forcing the fluid to flow upward and downwards between the tube bundle. Baffle spacing is of large thermodynamic concerns when designing shell and tube heat exchangers. Baffle must be spaced with consideration for the conversion of pressure drop and the heat transfer. For thermoeconomic optimization, it is suggested that the baffles be spaced no closer than 20% of the shell's inner diameter. Having baffle space too closely causes a greater pressure drop because of fluid redirection. Consequently, having the baffles spaced too far apart means that there may be cooler spots in the corners between baffles. It is also important to ensure the baffles are spaced close enough that the tubes don't sag. The other main types of baffle is the disc and the donut baffle, which consists of two concentric baffles. An outer wide baffle looks like a donut, whilst the inner baffle is shaped like a disc. This type of baffle forces the fluid to pass around each side of the disc, then through the donut baffle, generating a different type of fluid flow. And the next one is tubes and fine design. In application to cool air with the shell and tube technologies such as intercooler, charged air cooler for a combustion engine, the difference in heat transfer between air and cold fluid can be such that there is a need to increase heat transfer area on air side. For this function, fans can be added on the tubes to increase heat transfer area on air side and create tubes and fins configurations. Fixed tube liquid cooled heat exchanger, especially suitable for marine and harsh applications, can be assembled with brass shells, copper tubes, brass baffles, and forged brass integral and hubs. And what about the plate? Plate is a heat exchanger. Another type of heat exchanger is the plate heat exchanger. These heat exchangers are composed of many thin, slightly separated plates that have very large surface area and a small fluid flow passage for heat transfer. Advances in gases and brazing technology have made the pellet type heat exchanger increasingly practical. In HVAC applications, large heat exchangers of this type are called plate and frame. When used in open loops, these heat exchangers are normally of the gasket type to allow periodic disassembly, cleaning, and inspection. There are many types of permanently bonded plate heat exchangers, such as deep brazed, vacuum brazed, and welded plate varieties, and they are often specified for closed loop applications such as refrigeration. Plate heat exchangers also differ in the types of plates that are used and in the configurations of those plates. Some plates may be stamped with chervil, dimpled, or other patterns, where others may have machines, fines, and or grooves. When compared to shell and tube exchangers, the stack plate arrangement typically has lower volume and cost. Another difference between the two is that plate exchangers typically serve low to medium pressure fluids compared to medium and high pressures of shell and tube. A third and important difference is that the plate exchanger employ more countercurrent flow rather than a cross current flow, which allows lower approach temperature differences, high temperature changes, and increased efficiency. Plate and shell. A third type of heat exchanger is a plate and shell heat exchanger, which combines plate heat exchanger with shell and tube heat exchanger technologies. The heart of the heat exchangers contain a fully welded circular plate pack made by pressing and cutting round plates and welding them together. Nozzles carry flow in and out of the plate pack. The plate side flue pass. The fully welded plate pack is assembled into an outer shell that creates a second flue pass. The shell side. Plate and shell technology offers high heat transfer, high pressure, high operating temperature, compact size, low cooling, and close approach temperature. In particular, it does completely without gasket, which provides security against leakage at high pressures and temperatures. And what about the adiabatic wheel? A fourth type of heat exchanger uses an intermediate fluid or solid store to hold heat, which is then moved to the other side of the heat exchanger to be released. Two examples of these are adiabatic wheels, which consist of a large wheel with fine threads rotating through the hot and cold fluids and fluid heat exchangers. The next is plate fin. Pellet fin heat exchanger. This type of heat exchangers uses sandwich passages containing fines and increase the effectiveness of the unit. The designs include cross flow and cutter flow, cooked with various fin configurations such as straight fines, offset fines, and wavy fines. Pellet and fine heat exchangers are usually made of aluminum alloys which provide high heat transfer efficiency. The material enables the system to operate at a lower temperature difference and reduce the weight of the equipment. Pellet and fine heat exchangers are mostly used for low temperature services such as natural gas, helium, and oxygen liquefaction plants, air separation plants, and transport industries such as motor and aircraft engines. And what about the advantages of plate and fin heat exchangers? High heat transfer efficiency, especially in gas treatment, larger heat transfer area, approximately 5 times lighter in weight than that of shell and tube heat exchanger, able to withstand high pressure. And what about the disadvantage of a plate and fin heat exchanger? The first disadvantage is that might cause clogging as the pathways are very narrow, difficult to clean the pathways. Aluminum alloys are susceptible to mercury liquid uh, enrichment failure. And what about the fine tube? The usage of fines in a tube-based heat exchanger is common when one of the working fluids is a low-pressure gas and is typical for heat exchangers that operate using ambient air such as automated radiators and HVAC air condensers. Fines dramatically increase the surface area with which heat can be exchanged, which improves the efficiency of conducting heat to fluid with very low thermal conductivity, such as air. The fines are typically made from aluminum or copper since they must conduct heat from the tube along the length of the fines, which are usually very thin. The main construction types of fin tube exchangers are: the first one, a stack of evenly spaced metal plates act as the fines, and the tubes are pressed through pre-cut holes in the fines, and good thermal contact usually being achieved by the formation of the fines around the tube. This is typical constructions for HVAC air coils and large refrigeration condensers. Fines are spiral wound onto individual tubes as a continuous strip. The tubes can then be assembled in banks, bent in a serpentine pattern, or wound into large spirals. Zigzag metal strips are sandwiched between flat rectangular tubes, often being soldered or braced together for good thermal and mechanical strength. This is common in low pressure heat exchangers such as water cooling radiators. Regular flat tubes will expand and deform it if exposed to high pressure, but flat microchannel tubes allow this construction to be used for high pressures. A stack fine or a spiral wound construction can be used for the tubes inside shell and tube heat exchangers when high efficiency thermal transfer to a gas is required. In electronics cooling, heat sinks, particularly those using heat pipes, can have a stacked fine structures, and the next type is pillow plate. Pillow plate heat exchanger. A pillow plate heat exchanger is commonly used in the dairy industry for cooling milk in large direct expansion stainless steel bulk tanks. Nearly the entire surface area of a tank can be integrated with this heat exchanger without gaps that would happen between pipes welded to the exterior of the tank. Pillow plates can also be constructed as flat plates that are stacked inside a tank. The relatively flat surface of the plates allows easy cleaning, especially in sterile applications. The pillow plate can be constructed using either a thin sheet of metal welded to the thicker surface of a tank or vessel, or two thin sheets welded together. The surface of the plate is welded with a regular pattern of dots or a serpentine pattern of weld lines. After welding, the enclosed space is pressurized with sufficient force to cause the thin metal to bulge out around the welds, providing a space for heat exchanger liquids to flow and creating a characteristic appearance of a swelled flue formed out of metal. And what about the waste heat recovery units? A waste heat recovery unit or VHRU is a heat exchanger that recovers heat from a hot gas stream by transferring it to a working medium, typically water or oils. The hot gas stream can be exhaust gas from a gas turbine or a diesel engine or a water and waste gas from industry or refinery. Large systems with high volume and temperature gas streams, typically in industry, can benefit from a stream ranking cycle or SRC in a waste heat recovery unit, but these types and these cycles are too expensive for small systems. The recovery of heat from low temperature systems require different working fluids than steam. The organic ranking cycle or ORC waste heat recovery unit can be more efficient at low temperature range using refrigerants that boil at lower temperatures than water. Typical organic refrigerants are ammonia, pentafluoropropane, and toluene. The refrigerant is boiled by the heat source in the evaporator to produce superheat vapor. This fluid is expanded in the turbine to convert thermal energy to kinetic energy that is converted to electricity in the electrical generator. This energy transfer process decreases the temperature of the refrigerant that it runs condenses. The cycle is closed and completed using a pump to send the fluid back to the evaporator. And what about the dynamic scraped surface? Another type of heat exchanger is called dynamic scraped surface heat exchanger. This is mainly used for heating or cooling with high viscosity products, crystallization process, evaporation, high cooling applications. Long running times are achieved due to continuous scraping of the surface, thus avoiding fouling and achieving a sustainable heat transfer rate during the process. And what about the phase change? In addition to heating up or cooling down fluids in just a single phase, heat exchangers can be used either to heat liquid to evaporate or boil, or used at condensers to cool a vapor and condense it to a liquid. In chemical plants and refineries, reboilers used to heat incoming feed for distillation towers are often heat exchangers. Distillation setups typically use condensers to condense distillate vapor back into liquid. Power plants that use steam driven turbines commonly use that heat exchanger to boil water into steam. Heat exchangers or similar units for producing steam from water and often called boilers or steam generators. In the nuclear power plants called pressurized water reactors. Special large heat exchangers pass heat from the primary reactor plant system to the secondary steam plant system, producing steam from water in the process. These are called steam generators. All fossil fueled and nuclear power plants using steam driven turbines have surface condensers to convert the exhaust steam from the turbines into condensate water for reuse. To conserve energy and cooling capacity in chemical and other plants, regenerative heat exchangers can transfer heat from a stream that must be cooled to another stream that must be heated, such as distillator cooling and reboiler feed preheating. This term can also refer to heat exchangers that contain a material within their structure that has a change of phase. This is usually a solid or to liquid phase due to a small volume difference between these states. This change of phase effectively acts as a buffer because it occurs at a constant temperature but still allows for the heat exchanger to accept additional heat. One example where this has been investigated is for use in high power aircraft electronics. Heat exchangers functioning in multi-phase flow regimes may be subject to the leading instability. And here you can see the console software simulation shell and tube heat exchanger. And you can see the material that I have used is water as a liquid phase, air, and steel. And the physical module that I have used is turbulent flow with coepsilon and heat transfer in fluids. And you can see that this is compressibility, and turbulence mode is RANS AVM with coepsilon for the degrees. We have a inlet for water, outlet for water, and also inlet and outlet for air. There is a symmetry and interior walls. The next is heat transfer in fluid. You can see again inlet and outlet for water and air. And we have a multi-physics for non-isothermal flow. And what about the result? We have a velocity, pressure. You see that the pressure in the side of inlet and outlet, wire resolution. And the next result is temperature based on Kelvin. The maximum is 80 degree of Kelvin, and the unit its maximum, it says degrees of centigrade. It's a degrees of centigrade. And temperature and fluid flow here is based on Kelvin. I can see the arrows and how it transfer to the heat exchanger. Wall lift off and temperature along a streamline. And also we have a streamline here. You see that how this stream go and pass through the outlet and inlet, and this is the based on degrees of centigrade. Thank you so much for watching my tutorial video until the end. Also, you can download this simulation from github.com/mahsa